Hello everyone. Today our shared research is a dual product profit maximization model, with Starbucks latte and Frappuccino pricing as our case study. Product pricing is not just guesswork. It is a mathematical optimization problem, especially for shops selling multiple substitutable goods. Next, I will walk you through our full group analysis step by step. Let's start. Mamishi, I'm going to illustrate why pricing is essentially a mathematical problem, with Starbucks drinks as our practical business case. All businesses face a daily core question: how much should we price our products? If a store only sold one item, we only need basic calculus to find the maximum value of a single variable profit function. But real-life retail is more complicated. As we see on this Starbucks menu, cafes sells many interchangeable drinks at once. A price change of one beverage will shift customers' choices for others. Profit then becomes a multivariate function with connected price variables, which requires multivariable calculus to analyze. This brings us to our simplified research example. Now let's focus on our specific case: a coffee shop selling two core products, latte and frappuccino. These partial substitutes represent perfect alternatives. Latte are daily regular coffee, hot or iced, while frappuccino are sweet cold blended treats for leisure. Even with clear taste differences, price adjustments will still affect each other's sales. If we raise the price of latte, some customers will turn to frappuccino instead. This leads to our key business question: we cannot set their price independently. We need a pair of prices for both drinks to maximize total profit. To solve this, we set three clear research objectives on the next slide. Our whole analysis is divided into three complete steps. First, we build a mathematical model to show the relationship between price, sales, and profit for both drinks, including cross-demand influence between the two products. Second, we use partial derivatives and critical points analysis for multivariable calculus. We calculate critical points and verify them to find the optimal price combination that maximizes overall profit, replacing random guesses with strict math calculations. Third, we translate our numerical results into practical business implications for coffee shop operation. We will also cover the limitations of the simplified model and propose feasible improvements to make it real market situation better. With this clear framework, we can move on to build and solve our profit optimization model next.
Thanks for my teammate. I'm Zhu Junyu. My student ID is BSC2509069. So now let's actually build a model. First, the variables. We use PL and PF for the price of latte and frappuccino. These two are what we're trying to decide. So they are our two independent variables. QL and QF are the daily sales of each drink, and pi is the total daily profit. Notice right here, the problem is already different from what we usually do. We have two things to choose at the same time, not one. So actually, this is exactly why this becomes a multivariable problem. Next, we need to describe how sales respond to prices. Here are our two demand functions. Let me walk through the latter one. The 800 here at the front is the market size, roughly how many people would want a latte if it were free. The minus 40 PL term is just the law of demand. The expensive the latte gets, the fewer we sell. Nothing surprising. The most interesting part is the third term, plus 15 PF. It's positive. This is say that when Frappuccino gets more expensive, latte sales actually go up, because some customers switch over. This is the substitution effect that my teammate has mentioned earlier. And this single term is what we connects the two products together. Without it, we just have two separate one variable problem. The Frappuccino equation works the same way, just with its own coefficient. And here is also a notice. These numbers are all assumed for demonstration. They are not real data from Starbucks. In practice, it estimates them from the sales records. Now we build the profit function. The logic is simple. Profit equals price minus cost times quantity summed over both products. Unit cost is 6 ringgit for latte and 8 ringgit for frappuccino. Then we substitute the two demand function in expand and combine like terms. I won't go through the algebra line by line. The full expansion is in appendix. But the result is this, a quadratic function in two variables. Both square terms are negative, and there's a closed term, 25 PLPF, which again reflects the interaction between the two products. At this point, something important has happened. The business questions how should we price two competing drinks has been fully translated into a pure math questions. Find the maximum of these two variable functions. And before we solve it, let's be upfront about the assumptions. This is what makes our problem solvable. The first one is linear demand. The second one, that unit costs are constant. The third one, competitors don't react. For one, no seasonality, and prices can take any value. This keeps the model solvable. And my teammate will come back to discuss what we lose by making them. So with the model set up, the question is now, how do we actually find the maximum? That's over to my teammate. Thank you.
Now, this is conclusion part. Junyu already gave us the profit function, pi of PL and PF. Next step, it is partial derivative. What is partial derivative? Simple. We fix one variable, look at the other one only. So we fix PL, look at PF only. This is called partial pi over partial PF. Rules are the same as normal derivative. Minus 14PL squared becomes minus 18PL. 25PL/PF, we treat PF as a constant, so it becomes 25PF. And 916PL just becomes 916. Same way for PF, we get the second equation, so now we have two partial derivatives. They show how profit changes in each direction. So, what's the condition for maximum? At maximum point, profit should not increase anymore in any direction. So both partial derivatives should equal 0 at the same time. We set the two equations to 0 and get this system of equations. This is different from one variable calculus. One variable, we only need one equation, but here we have two variables, PL and PF, so we need two equations together and to solve both. Now we solve this system. Just use substitution, same as high school algebra. From equation 1, we solve PF in terms of PL. We get PF equals 3.2 PL minus 13A.4. Substitute into equation 2. Simplify, we get minus 199 PL plus 3,014,478 equals 0. Solve it. PL is approximately 17.48. Substitute back, PF is approximately 17.53. So now we have 1 point, 17.48 and 17.53. This is the critical point, but it's just a candidate right now. Could be maximum, minimum, or neither. So next, we need to test it. This step is the most important one. We check if this critical point is really a maximum. First, we calculate 3 second partial derivatives. pi LL equals minus 18, pi FF equals minus 17, pi LF equals 25. Then we need to use these three numbers to get a value D. D equals pi LL times pi FF minus pi LF squared. We get D equals 4,019,975. This is greater than 0. So if D is greater than 0 and pi LL is less than 0, then the point is the local maximum. Both things are true here, so this is converted as a local maximum. Also, these three numbers are constant. They don't change with price, so this stays true everywhere. That means the profit function is concave everywhere. Just one peak. So this local maximum is actually the global maximum too. Last step, we substitute the optimal prices back. We plug PL 17.48 and PF 17.53 into the demand function. We get QL approximately 363.75, QLF approximately 161.25. Then substitute into the profit function, the final maximum profit. Pi is approximately 5,713 Rm. So basically, when latte is priced about 17.48 Rm and Frappuccino about 17.53 Rm, the coffee shop gets its highest daily price around 5,713 Rm. So this is my part. And now over to D. They will explain what this means for the business. Thank you.
Hello, I'm Yang Pengyu, BSC130 I'm responsible for Part 4, Results Analysis. So, Part 3 gave us the optimal prices, about 17.48 Rm for latte, 17.53 Rm for Frappuccino. Notice they are almost identical, not a coincidence, because they are substitutes. If the price gap is too big, everyone buys the cheaper one, and total profit drops, so the model puts them together. For substitute products, joint pricing makes prices converge. What if we price them separately? The comparison is that joint pricing gives us about 5,730 million, but independent pricing, ignoring substitution, drops profit by roughly 5 to 8%. The exact number doesn't matter. The point is, optimizing one product in isolation gives you the wrong answer. That's why we need multivariable calculus. Products in reality are never isolated, and single variable calculus can't handle these interactions. Of course, the model has limitations. Let me run through them quickly. 1. Linear demand. Real demand is often non-linear. 2. No competitor response. 3. No seasonality. 4. Consistent costs. Not always true. 5. Continuous prices. But real prices move in steps, like RM0.1 or RM1. These assumptions make the model solvable, but they also mean it can't be directly applied to the real world without caution. How to improve it? There are 3 directions. First, use a vector function to make prices dynamic over time. With Frappuccino in summer, latte in winter. Second, use infinite series to model customer lifetime value. Third, use double integrals for sensitivity analysis to check stability. These upgrades move the model from static to long-term strategic. Let's move to the conclusions. First, partial derivatives and the Hessian successfully found the optimal prices. The method works. Second, and the most important, multivariable calculus handles product interactions that single variable calculus simply can't. Third, in reality, products are always connected, so joint optimization is always better than isolated. That's all. And there are our references. Thank you for listening.